So welcome to lecture 40 of MCS 472. So in this lecture we are going to consider face recognition and the ranking of data, as one needs to do when you want to build a search engine. So face recognition also falls within machine learning. So these two problems are seemingly very disjoint, but mathematically there is the eigenvector eigenvalue problem that is the connection between the two. So as far as machine learning goes, we have covered the principal component analysis, and it will all boil down to setting up this computation of the dominant of the most important eigenvalues and eigenvectors. The same for the PageRank. The PageRank problem can be, and I would say mathematically, recast as an eigenvector problem. So let's do this then. What is the problem with face recognition? So face recognition is a very well studied problem, and many automated systems have already been developed for this. It is a very challenging problem. One has the position of the head that can be can be at several angles, and it is essentially a three-dimensional problem, and you try to do this from a two-dimensional picture. There are the lighting conditions, and then you still have the same face when you smile or not, and there are several other expressions that can drastically alter a face, but it's still the same face. The method that we are going to apply or discuss here is a linear algebra approach, which goes back to 1987. So it leads to eigenfaces. So, and how can this problem be dealt with? Well, on input we have a grayscale image. So in a way, it's important already that the reduction from color to grayscales and the extraction of backgrounds is dealt with. So we have images that are now living, so the images are matrices of numbers. So we have a resolution, and that resolution determines the dimension of the space of all the images that one can make of that size, of that format. Now it turns out that this problem has the characteristic that if you look at the subspace of images that come from faces, that actually has a low dimension, a relatively low dimension that is independent of the resolution of the pictures. So that's a result that is described in this paper referenced here on this slide. So in this lecture we take a mathematical view. So I take a paper from the SIAM review, SIAM for the Society for Industrial and Applied Mathematics. And the title hints at the singular value decomposition. So there are other approaches. We've covered neural networks, and the other approaches I will list later. But with neural networks, one has to decide on the number of layers and what happens at every layer. With the eigenfaces approach, we will get to something that is, it's at the bottom here of this slide. You have what is a rank, or the relevant components in the image, essentially. Okay, we start from an image, a P by Q matrix, now as floating point numbers, and we consider what is known and widely known in linear algebra at least as a singular value decomposition. So we decompose the matrix as a product of three matrices. The first matrix U is orthogonal, a P by P matrix. The second matrix is a diagonal matrix. This matrix will contain the singular values, and we typically sort them. The first singular value is the largest singular value. And then the third matrix in this singular value decomposition is again orthogonal. Orthogonal matrices are extremely important. We will see that they operate as projection operators. So throughout this course, and also this is the sequel to numerical analysis, we have applied orthogonality many instances. So this will be another instance where we apply orthogonality. So as far as this, so I mentioned on the previous slide that the number of vectors that you need to span the subspace, spanned by all facial images, is relatively low or modest compared to the entire subspace of all images. So if one looks now at exact matrices, then the singular value decomposition can be determined to define the rank of a matrix. So the rank of the matrix is the number of singular values that is not zero. Should also have pointed out here is that all the singular values are actually positive. Okay, so the singular value decomposition is our major tool. So I mentioned that the position of the head is kind of important. Here is a geometric interpretation of the singular value decomposition. So we multiply some data with the matrix. So the multiplication then goes actually from right to left. So we actually first multiply with the third matrix. And if we start, say, with a circle, then it corresponds to rotating the circle, which here you could see on the picture it's equivalent to rotating the coordinate basis to the vectors contained in the columns of this third matrix. What the singular values do is that they are stretching the circle. So having a circle, I should have pointed this out sooner. If you do the singular value decomposition on an orthogonal matrix, all the singular values will be 1. So you can associate, so orthogonal matrices are very nice matrices. They correspond to spheres, or here with 2 dimensions, to circles. So the magnitudes of all their eigenvectors are also 1. Okay, so then we have the ellipse that gets rotated at the third stage in this multiplication. So the reduction of the matrix is from a general matrix is reduced to the matrix of singular values by the pre and post multiplication of 2 orthogonal matrices. We will use this geometric interpretation to justify the pre-processing of the data. Okay, so I misspoke a couple of times in referring to eigenvalues and eigenvectors, but they actually come in very naturally. So if we have this singular value decomposition, so if we multiply both sides in this equation here by the right, by this third matrix, V transpose V equals the identity matrix, then we recognize already the shape of a singular value decomposition. So we also have the important property that the singular value decomposition measures what the matrix does to unit vectors. So we see the matrix as an operator. It takes vectors from one space to another space, and matrices with all the singular values equal to 1, they are not going to stretch the unit vectors. So the largest singular value can be interpreted as the magnitude of that operator A. So it says what the matrix does to unit vectors, how much they get stretched out. In numerical analysis, we related this to the definition of the condition number of a matrix. Okay, it also says something about the magnitudes of the numbers that are stored in the matrix A. So here is an exercise. So one can, with some rewriting, one can show that the columns of V contain the eigenvectors of A transpose A. So the first identity here at the bottom left gives an interpretation of the columns of V. V, by the way, is an orthogonal matrix. So we have an orthogonal basis of eigenvectors of A transpose A. And the second identity at the bottom right of this exercise says that the columns of the matrix U are the eigenvectors of A times A transpose. So A is P by Q, A transpose is Q by P, so the A times A transpose T is a P by P matrix, and that was also the definition of the dimension of the matrix U. The same for why do we do A transpose A? Well, A is again P by Q, so A transpose is Q by P. A transpose times A is a Q by Q matrix, and that was also the dimension of Q, was the dimension of the square matrix V. So we're going to use that property. You can see that if you are only interested in, say, the U or the V part, then you can compute the matrix, the U part, independently of the V part. Okay, what is now the relationship to machine learning? So in this course we are using Julia, and I was looking up how this could be done in Julia, and I came across a poster presented at the Julia conference in 2020, which lists principal component analysis as an alternative to the histogram-oriented gradient method and the convolutional neural networks approach. So when we discussed neural networks, I was using another Simon review paper, and that also introduced the convolutional neural networks approach. So I just want to say, in this lecture, we are heavily oriented towards linear algebra, but linear algebra and the eigenvalue method features is actually the principal component analysis of machine learning. Okay, so following the other paper, so by Neil Muller and all, in SIME review, I will illustrate the procedure, which is very similar to machine learning in the sense that one works with a training set. and that one uses a subset of an image database. Here, that image database consists of color images, but it allowed them to extract the background, and when the images were then converted to grayscales. So the training set contained pictures, three different pictures of 200 individuals. So the training set is used to determine the size of the dimension reduction. So that's the advantage of the approach. So we will test the reduction of the dimension. So we have the dimension corresponding to the resolution, and then facial images are kind of special images, and they can represent it in a smaller subspace. So that was the key idea why this works. Now, of course, you cannot apply this directly. So here is the covariance matrix that comes up. So now to introduce the idea of covariances, suppose that you would be a lot more restrictive. Instead of a picture, an image of a face, you would classify faces to measuring the width and the height. So you have two numbers. Now, if you were to, so x is the width, y is the height, then if you were to represent this geometrically by dots in the plane, then you may see that this corresponds to an ellipse. So, and then one can normalize the data set by computing the mean and placing the coordinates, the origin of the coordinate system at the center of the observed data, which will have somehow an ellipse shape. And then one can still do a coordinate transformation by going over to the principal components, to the main directions in the observations. And that is done on the shifted matrix via a singular value decomposition. So this is important to normalize the numbers. So here is the procedure more spelled out in detail. So we compute the mean of all the observations. We shift the data. So now we have a matrix of 2 rows and n columns. We will take into account the standard deviation, so we will still divide by the square root of the number, and then we will compute a singular value decomposition. And the first 2 columns of this matrix U, now remember this exercise. So the matrix A was P by Q. A transpose is Q by P, so we did A transpose A. And that's actually the covariance matrix. So we do the singular value decomposition on the covariance matrix. Or actually, with this exercise, the columns of U actually gave the eigenvectors of the matrix A transpose A. And in some sense, it looks very algorithmic and mathematical. One can also give a statistical interpretation that with the ellipse, one can already one already has some kind of a classifier. So it may be it is intuitively clear that if you do another measurement, so what is in the ellipse is the test set, is the training set. If you have a new picture, and if it turns out that the measurements are more at the outside of the ellipse, and then the thing, if it is a face, although it might be not likely that it is a face, but it is less likely to be a normal face. So that is another very basic classification of faces just by using two measurements. Alright, we will use the very same idea to arrive at the concept of eigenfaces. So this slide is central to defining the linear algebra approach. We have images as matrices, but we will stack all the columns in the image in one long vector. So P by Q, you can think of 100 rows, 100 columns, which gives us 10,000 numbers. So in 100 by 100 might not be such a big resolution for an image, or can be standard a resolution, and that will be reduced dramatically, almost by a factor 100, by using the subspace of all facial images. So here you see the 4 steps, the same as what we did with the principal component analysis, repeated again here. So we compute essentially the covariance matrix, and we compute the eigenvectors. Now it turns out that I misspoke earlier. So actually the covariance matrix here for U is A times A transpose, not A transpose A. Okay, so then how does this all work? Well, we have the mean from the entire singular value decomposition. It will actually turn out that if you compute a singular value decomposition, you can stop your algorithm after the most dominant, the largest singular value. So we will only take the first mu eigenvalues, new eigenvalues. So mu is the mean, nu is the number of eigenfaces that we consider. We can then take the first new columns of the orthogonal matrix U, and that defines a projection operator. So here we go again to essentially the orthogonal projection. This has been applied over and over again in this course. So we have an orthogonal space and we project any image onto that space after subtracting the mean of the training set. And then we can reconstruct, we can do the inverse. So we take the transpose of the matrix U sub nu. The inverse is the original matrix, and that is used to reconstruct. So we have our training set. In this case, it were 600 images, and with that training set, one can look at the images again and see how much they resemble, how much the reconstructed images resemble the original images, and that gives somehow an idea on how to choose the value for nu. Okay, and we recognize this procedure from way back. So last week, essentially, lecture 37, where the principal component analysis was explained by these 3 steps. Back then I mentioned the QR algorithm to compute the principal components. And that's what you can do to compute the main columns, the first new columns of your matrix U. Same mathematics, entirely different application area. Okay, so let's now look into another class of applications in ranking data. So consider the search engine problem. One has a search query from a user, and one has web pages where those queries words appear. So one can present the user with these links. The problem is that there are an immense set of web pages, and how to order those pages. Which pages are most important to the user? There's also an urgency to this, so you don't want the user to go through all your results, but also you want to do this sorting extremely fast. So it's also an engineering challenge. So the approach in this lecture, so the point of view is the applied math lecture. I must say that many real problems also are engineering problems. So the first paper that is cited here describe more the engineering problems. I will be following the second paper in defining the PageRank. So how one can essentially reduce this to an eigenvector computation. Okay, so what is the PageRank? Well, the crawlable web, so the web itself can be thought of as one giant graph or a network. The nodes in the network are the web pages. The links between the pages, whether one page refers to another page, is an edge between nodes in the graph. So what is then the intuitive notion of when is a page more important than the other? Well, you look to the connections. So it's a directed graph. Pages refer to other pages. So these are the out edges, so the forward links, and they're also incoming edges. So pages that are referring to a certain page. So these are called the backlinks. So it is clear that pages that are highly linked, they are the most important pages. So one will use that criteria. Okay, so then for every web page, one collects the set of the pages that page is pointing to, and one also collects the set of the back links, the nodes that are in the backlinks. So the notation capital F refers to the forward links. So all the pages that the page U is pointing to, and then the capital B is for the backlinks. So the ranking, what is here the simplified page rank, is for every page there is a rank associated which runs over all the backlinks. So the importance of a page is the sum of all the importance of the pages that point to it. So it looks like it is recursive. So the R is at the left, the R is at the right, but note that the R at the right is applied to the pages that are referring to U. And the more important that a page is that refers to U, the more important that page is. So the more, so you can also, the U can also apply to you as a person. So you are important if many people say that you are important, and the more important those people are, then you, the more important that you are. So one can rank many items like that. So this is a very, and I'm just now referring to you, not to you as an item, but you get the point here. So this page rank is a very natural model. So there are some scalings here. So one divides by the number, the number of pages uh, in the forward links. So that's the denominator here. And there is also another scaling, another normalization factor. Okay, we can, so that's a definition which makes quite sense to us. It's simplified, it's not really an accurate model, but it will do to get at the eigenvalue, eigenvector problem. Look at this problem now. So I said that we can look at R as a function that gives for every page a score, but you can also see this as one vector. So you can consider this as one column, and one can then see this definition as at the left you have one column vector, and at the right you have a matrix vector multiplication. So I listed here in the definition the main actors, but based on this we can define a square matrix that contains, that is essentially the adjacency matrix of the network. So we have a zero element if there is no link between two pages. Otherwise, we list the number of pages that the page is pointing to, 1 over that number. So it's a floating point matrix. So the definition of the simplified PageRank then can be written as a matrix vector multiplication. So there is this R equals CAR, so the car. You can rewrite this a little bit and say that the PageRank vector is an eigenvector of the adjacency matrix. Not quite the adjacency matrix, but it's a weighted adjacency matrix, weighted with the importance of the nodes, the number of nodes. Okay, I said it was a simplified PageRank. So here is the problem. You may have what is called a rank sync. So what you could have is that two pages that are pointing to each other, but they're not pointing to any other page. So if you get into there, then you end into some kind of a subspace of the internet. So if you would start browsing and you would follow the links, you would actually never get out. Now, this is very unrealistic if you have ever browsed the web. If you observe that you're getting in a circle, you will point out. So to avoid this and this model then of the PageRank takes this into account. So in order for avoiding these rank sinks, we're going to add a correction term. And the correction term depends on some vector that corresponds to the source of the rank. And we will now also maximize the PageRank vector so that the one norm equals 1. And now again, we still have an eigenvalue, eigenvector problem. So it's not clear from here, not exactly an eigenvalue problem, but we will reduce it to an eigenvector problem. So I'm still following now I'm following the random surfer model. So there is another interpretation for this correction term, and it can be interpreted by the likelihood that when a surfer ever, if you're surfing the web and if you notice that you are into a loop, then there is this likelihood that you will jump out, that is with this model by this E. So with the random surfer model, we will be able to give a better interpretation for this formula here. So this formula, which is now the R prime, it's not the derivative, it's just another letter for R. So it's a corrected model, if you write. The computation of the PageRank is computing the eigenvector associated with the dominant eigenvalue. So I copied this this algorithm from the PageRank definition paper. You see that this algorithm, even if we would not see the connection with the PageRank, we recognize actually the power method, which we also discussed in numerical analysis. So we have the matrix vector multiplication, starting from some random vector, we multiply, and then we observe that that vector will converge to the eigenvector corresponding to the most dominant eigenvalue. Now, if you look at, so in numerical analysis, we normalized the vector every time because we were concerned with the growth of the numbers. Here we're actually not doing this. And why is it that we're not doing this? Well, that's the question for the second exercise. And in some sense, we will give the answer to that question. So why the algorithm to compute the PageRank is actually given like this. Now, again, ranking data is a very complicated problem, and we come up with here an extremely simple algorithm. The web has millions and millions of pages, so this matrix computation is actually a very, very huge computation. If you're not clever about storing and representing that adjacency matrix, then it is a hopeless task. Okay, so I said that we will solve the exercise. The matrix that we consider is actually a very special matrix. It's a stochastic matrix. So it made somehow sense that we normalized our numbers right from the beginning. So we were dividing by these denominators, this capital N factors. And that makes that the matrix that we consider, so here we will derive the PageRank in a different way. So imagining now a surfer, what is a surfer doing? Well, the surfer is situated at one page, so we call the page I for an index, a row index, and it goes. No, I'm sorry. So we are at the current page. We are looking at a column. The jade page is the page where we currently are, and we're moving to some page I. So, and we can collect the probability. So the jade column, so because it's a probability, that column needs to sum up to 1. So if we do this for all the pages, and we store all the probabilities in one large matrix, then we have what is called a stochastic matrix. And the simplified PageRank definition actually corresponds to this equation x equals c times p times x. So again, we now have the multiplication of a vector with a matrix, but that matrix is actually already quite normalized. So that's one intuitive reasoning why in the previous algorithm you would not need to be concerned about the growth of the numbers. Okay, so let's get at the so the simplified page rank was intuitively enough to understand, but the other model, the more realistic model, was actually not so. So I hope to explain this now. So we had the loop. So at some point, a surfer gets into a loop and will get bored and will jump out of this. So what is the probability that the at page J, the next move is on one of the out edges, is on one of the eyes for which there is a link? So, in some sense, a surfer can always say that what is on the page is not interesting, so I'm not going to follow any of these links. So, I'm going to jump out of this. So, that's the probability 1 minus alpha. And one says that the surfer then kind of teleports out of the page and does not follow any of the links on that page. So then actually we arrive at this modified equation involving the teleportation parameter and also involving the distribution of now over all the pages that are available. There is a probability associated with every page that the surfer will go there. And that probability distribution is also essentially related to the importance of every page. Okay, so let's make that clear. So now this is an alternative definition of the PageRank vector. So we have a stochastic matrix where the columns are the outlink probabilities for every web page. We have the teleportation constant and the distribution of the probabilities of a teleportation. So if a surfer decides not to use any of the links on the Jade page, what is the probabilities that it goes to another page? So with this, we can then derive the equation that characterizes the PageRank vector. So the PageRank vector satisfies this equation here. So this reduces the PageRank problem to solving a linear system. But as will become in a minute clear, we can rewrite that equation solving a linear system to an eigenvector problem. And here it is. The distribution of that when teleportation happens, that distribution vector is again a probability vector. So all the entries have to sum up to 1, and we will use this property. So if you have V E transpose, so the PageRank vector itself is also a stochastic vector. So that is actually what becomes clear from this reasoning, and also which indicates is actually also the solution to the exercise. So the reason why everything works out on such a grand scale is that the vectors that we are working with are actually always normalized. So they're stochastic vectors. The sum of the probabilities equals 1. Okay, I'm near the end of this lecture. So beyond PageRank, so we all use search engines, and we're happy to understand now a little bit why it works, at least mathematically. Now, this idea of ranking the data appears in many applications. So here I listed some of them. So there is bioinformatics, gene rank, and protein rank. One can look at different graphs and try to figure out in what sense are the graphs actually the same. In what sense are they isomorphism? Um, One can also apply this to dependencies of software, of large software systems. So, maintaining large software systems is often a nightmare because when some function changes, it propagates through an entire system. So, one can actually see the Linux kernel as a network where the nodes are the functions and then the links are the connections between the functions. In this course, we considered traffic. So one can uh, also apply this PageRank model to traffic. Um, so one also has winner networks in sports. You may have, if you are um, using a streaming service for watching movies. After you watch the movie, you may receive a recommendation, and recommender systems are also in use there. So you may see that after a while, if you start clicking the on the movies, you may actually end up into a loop. So these rank syncs occur there. In academia, so I'm list here the recommender systems for books. So one can also make a network of authors. Two the authors are the nodes, and two authors are connected if they have written something together, if they are co-authors. One can kind of make ranks on that, and of course, importantly, for literature, one can, when one, there's Google Scholar, when one looks at a paper, one can check how many papers are actually citing this paper. The so we often use the reputation of a journal. Simon Review has a very good reputation, but you can also look at the Google Scholar rating. So a technical report like the one that I used for the PageRank, I cited that this was I saw that this was cited 16,000 times already. So even if it's not published somewhere, it's a technical report from a university, then it's still an extremely relevant and important paper. Okay, so this is lecture 40, so we are at the end of the course. Let me summarize what we have done. Um, so it looks like we have covered a little bit of everything, but we started with statistics, quality control, Monte Carlo, and actually with machine learning, there's no clear boundary between statistics and machine learning. So today we have seen orthogonal projections. They have featured many times. So with the fast Fourier transform, the discrete transform to describe signals. So there is a regression. We've seen the basis of Chebyshev polynomials, the Fourier basis. They appeared again in the partial differential equations when we looked for solutions of differential equations. So there are some unified themes and methods that always occur and reoccur. So I listed 10 items here that we have discussed in this course, but most importantly, this was a project, or this is still a project-driven course, and the oral presentations and the writing of technical reports is certainly as important as the technical material. So I'm closing in on my 50th minute now in this lecture. I hope that this lecture was interesting, as was the course in itself. So thank you for watching this lecture.